Hello, my name is Thomas Deckman. I'm a student at North Carolina State University, and today I'm going to be discussing our recent results studying the Mott insulating phase transition on noisy cloud quantum hardware. Specifically, we've implemented an algebraic fast-forwarding circuit, which allows us to avoid some typical errors you get from Trotter approximations, entangling themselves with the noise from the quantum hardware. This work was conducted at North Carolina State University, Oak Ridge National Labs, and the University of Tennessee, Knoxville, and we want to acknowledge funding from the Department of Energy. This work is also available on arXiv. Unfortunately, we won't be able to get to every aspect of this study, especially some of the simplifications and optimizations. If you'd like to learn more, I encourage you to look through the arXiv link. The model we're interested in studying here is the Hubbard model. It's a simplified model of interacting electrons on a lattice. Each lattice site contains up to 2 electrons, one spin up and one spin down. And we simplify the Coulomb interaction to only on-site interactions. Electrons can also hop from one lattice site to another neighboring lattice site. We're interested in studying the Hubbard model and as large of a system as we can. Unfortunately, it is very difficult because it is an interacting many-body system. So you can really only get up to dozens of particles using classical systems. Dynamical mean field theory is a development which provides a mapping from the Hubbard model to the Anderson impurity model. In the limit that the Hubbard model has infinite coordination number in the lattice, which means each lattice site is connected to an infinite number of other lattice sites, the Anderson impurity model can exactly capture the dynamics of the Hubbard model. Anderson impurity model is a model which has a single impurity site, which allows the electrons on the impurity site to interact. This impurity site is coupled to a bath of continuous energy levels. If we want to simulate the Anderson impurity model, though, it still allows some difficulties. The first is we need to discretize the energy levels. The second is we need to truncate the number of energy levels down to something more manageable. Because we're looking at noisy cloud quantum systems, we truncate this down to a single energy level. This is called the two-site Anderson impurity model. And significantly, despite its simplicity, it still captures some kind of remarkable physics in the system, especially looking at the Mott insulating phase transition. So as a comparison, using kind of more sophisticated methods, renormalization group and exact normalization, this parameter u, which is the coupling term between interactions, there's a phase transition at u equals 6 that is very well captured by this two-site DMFT system. While the dynamics away from u equals 6 are a little bit different from kind of a more sophisticated method, we can still see some very remarkable physics, which means this is a very interesting system to begin to study. The Hamiltonian is relatively simple. It has some hopping terms which preserve spin and interaction between the impurity sites. DMFT provides a framework for the mapping between the Hubbard model and the Anderson impurity model, but does not provide exact parameters. Specifically, the hopping term from the impurity site to the bath sites and the energy levels at each of these bath sites. For two-site DMFT, this epsilon value, this energy level, is fixed by symmetries, and so we're interested in finding the correct value of V, which corresponds to the Hubbard model we're going to study. To do so, we compute the self-energy function as a function of frequency, and use that self-energy function to update the value of V. We then plug that value of V back in, compute the self-energy function, and continue this iteration until the output V corresponds to the input V. Solving for this self-energy function, though, is unfortunately difficult, and this is where quantum computers come in. The idea is to use quantum computers to compute the value of Green's function in the time domain. We then can use classical systems to Fourier transform Green's function, compute the self-energy function, and compute the quasiparticle weight, which corresponds relatively directly to the value of V. Here, it's notable that while we compute Green's function in the time domain, we're interested in Green's function in the frequency domain. So this will kind of be an important aspect of our going forward. We want to compute the retarded impurity Green's function. The simplification of this down using symmetries and as many reductions as we can, we're able to reduce this down to the real component of a single expectation value. To compute this expectation value, we first prepare the ground state using kind of a minimal gate count VQE type circuit. We then plug this ground state into a Hadamard type interference circuit. So we prepare an ancilla in a superposition. We then interact the ground state with the ancilla. In this case, the A and B would be C naughts. We perturb the ground state. We time evolve this perturbed ground state in a superposition. We then invert the perturbation, and then we measure the ancilla. So this measurement on the ancilla allows us to compute this expectation value. The difficulty is in implementing this time evolution term, this U of t. And this is where something called Cartan decomposition comes in, which provides a mechanism of computing a fast-forwarding circuit. Key here is that the circuit that we end up with is fixed depth, which means increasing the time of the simulation does nothing to the kind of error that you generate within the circuit. It doesn't change any of the gate structure of the circuit. So we expect the error to be completely unentangled from times. The general framework for this is we find the minimal Lie algebra, which kind of spans the Hamiltonian. We decompose this minimal Lie algebra into a set of terms which are diagonalizable, and a set of terms which we can use to rotate the Hamiltonian into this diagonalizable basis. So we apply this rotation, which we call K, to this diagonalizable kind of Hamiltonian, which we can time evolve kind of freely because this diagonalizable Hamiltonian commutes with itself. And we then can invert that rotation. And if you'd like to learn more about this, I encourage you to look through this reference that I have on this paper page. Actually implementing this circuit on quantum hardware requires a lot of dramatic reductions. I would love to spend more time on all of these. Unfortunately, we don't quite have the time in the 10-minute talk here. However, the first simplification and the first kind of thing that we exploit is an understanding of the general structure of Green's function. In this case, it is two cosine functions, each with an amplitude and each with a frequency. So what we're really interested in is computing this alpha, this omega, alpha 1, omega 1, alpha 2, omega 2. However, quantum computers are not, especially noisy quantum computers, are not quite as good at preserving these amplitudes. So what we have done is reduce this calculation to only using frequencies, which, because we do not have kind of a noise dependence on the time, we're able to very well preserve frequencies in our signal. We can then also exploit different error mitigation methods and the structure of our Cartan decomposed circuit to dramatically reduce the gate count of our circuit. So where do we end up with? This slide represents data in the conducting phase, U equals 2. The orange data on the left corresponds to the ideal Green's function that we'd like to sample. The purple and the blue data correspond to the data that we get from kind of all of our error corrections put together on the quantum hardware. So we can see the data runs from about 5 times attenuated to about 15 times attenuated from this frequency that we're looking for. Because we have two different frequencies, we actually sample Green's function at two different rates, one at a kind of high sampling rate to get high frequency data, and one at a very low frequency rate to get a very low frequency data. So this low frequency sampling allows us to go out to a very long time, which we can do because we're using a fast forwarding circuit. We then Fourier transform these and extract the frequencies. We can kind of zoom into where we're expecting the frequencies to be here. So here we were able to compute the high frequency signal with relative accuracy, and we're able to compute the low frequency signal kind of using the separate sampling. In the insulating phase, we have something different, and this is where these kind of sampling rates comes into play. First, we compute the high frequency signal with relative accuracy over kind of a similar thing that we saw for the conducting phase. However, for the insulating phase, the low frequency signal converges to 0 through the DMFT loop. So what we have to do is compute Green's function over a very, very long time scale. So what we do is really kind of crank down the sampling rate to very, very low so we can zoom in as close to omega equals 0 as we can. So first we compute omega 2 using the Fourier transform, and then we can use the value of omega 2 to find the aliased signal that we get from undersampling the high frequency signal and kind of eliminate that from our data and accurately locate the low frequency signal. Fortunately, we're able to converge relatively rapidly to the solution that we're looking for. Here we have the kind of convergence behavior in the conducting phase and insulating phase. In both cases, despite kind of some noise from the system perturbing us from the convergence behavior that we're looking for, over time, over increased iterations, we do converge to the value of the quasiparticle weight in V that we're kind of expecting from the theory. Here's the ultimate results of all of this work, is computing this phase diagram, this DMFT phase diagram, over both sides of this transition point U equals 6. Unfortunately, we can't calculate it right at U equals 6 because of the difficulty in the kind of, you need to go out to a very, very large number of iterations to accurately converge, which is just infeasible on the quantum hardware right now. In this work, the really remarkable thing is that fixed depth circuits are able to very well preserve frequencies, even in the presence of kind of decoherent noise. So we're able to access very large timescales that Trotter based approaches are not able to access. And we're able to kind of build together lots of error mitigation methods and optimization methods to accurately kind of simulate this system kind of in the kind of limit of very high decoherence and very large noise in the system. And we're able to apply this fast forwarding circuit to a relatively large system on hardware compared to what's existing in the literature, and kind of demonstrate this physical process for the first time on quantum hardware. And again, I encourage you to read through the archive link, especially if you're watching this online, and to kind of see more about some of these methods. And also ask for any questions. Thank you very much.